and countries abroad. Today we're going to approach problem 1761, a minimum degree of a connected trio in a graph. 17 is the age that I started programming, so no, if you didn't start before you were like 11, like some of these nerds, there's still hope for you. And 61 is the age by which I hope to retire because trying to take a yacht around the Catalina wine mix. I don't know. Anyways, let's go ahead and get to this problem. So we're trying to find the minimum degree of a connected trio in a graph. What does that mean? I don't know. I haven't really read the problem yet. So let's just go and get into it. Okay, you are given an undirected graph, okay? You are given an integer n, which is the number of nodes in the graph, and an array edges, where edges I equals uvi, indicates that there is an undirected edge between ui and vi. Okay, cool. So it's already telling us right now, this is a graph problem. My favorite, what I can solve. Hopefully there's no dynamic programming or something trickery. Hopefully it's just a direct graph problem. Maybe a little graph traversal, something fun like that. A connected trio is a set of 3 nodes where there is an edge between every pair of them. Okay, so there's a triangle, right? So connected trio is like, hey, it's me, Mario. So I have these 3 nodes, right? They're all connected to each other like this. There's an edge between every pair of them, right? So this is a pair of nodes, there's an edge between them. This is a pair of nodes, there's an edge between them. And this is the last pair of nodes, and there's an edge between them. So yeah, I was just making sure that it has to mean that they're directly connected, right? Because you could also be like, if it wasn't that condition, then you could be like, well, this is a trio, right? This is a trio because they're connected, but no, they have to be directly connected. So like that. Okay. There has to be a direct connection. So triangles. There has to be triangles in the graph. That's what a trio is. The degree of a connected trio is the number of edges where one endpoint is in the trio and the other is not. Okay, so for this system here, right, if we had additional edges, maybe coming out of here, I do not know why I circled this. Okay, like that, right? Where one endpoint is in the trio and one is not. Okay, so this is a part of the degree because one endpoint of this blue connection is inside of the trio while the other is outside of the trio, right? Same with these additional ones that I'm coloring now, right? These are also degrees because one end is in the trio while the other is not. Versus these connections here, right here, and here, and here. Both ends of these edge connections are in the trio, right? Because if both ends connect to these green nodes, right, they're both ends are in the trio, so they're not counted. So the degree of this example would be 1, 2, 3, 4, 5. 4, 5. Okay? So I think before we even continue, okay, well, return the minimum degree of a connected trio in the graph. Okay, so there's really 2 stages to this problem just right off the bat I can think of. First, we need to find all trios. And second, we need to calculate the trio's degree. Well, when we look at the basic idea of a degree of something, right? Like this has degree 3. We'll do a different color. Just go with yellow. So this has total degree 3, not trio degree. I'm just talking about this node, right? Because there's 3 edges coming out of it. I can't count. There's 4 edges coming out of this one, right? And there's 4 edges coming out of this one. So the total degree of this trio is what? So we can get the total degree of this system of every node by taking the count. So we take the sum of the degree at each node and we divide it by 2. Now, why do we divide it by 2? Well, because we overcount, right? So for this edge here, right, we're going to end up counting it twice because we're going to count it once for this node and we're going to count it once for this other node. So we need to divide by half because every node will get counted twice because every node inside, right? The edge touches both sides, so it adds the degree components to both sides, so it's counted twice. So we divide it by a half so that we only count every edge once, right? So for this system, we have 1, 2, 3, 4, 5, 6, 7, 8, right? So there's 8 total edges, right? And then we want to eliminate the red edges, right? Because they aren't a part of the trio. So for any trio, there's going to be 3 additional edges that create the trio, right? No such other link can exist, right? So the edge weight is in this minus 3. Does that make sense? Because we count all the edges, we divide it by a half, and that will give us the total degree of this trio system. But we don't want to count the edges that are both connected to endpoints of the trio, right? These red ones, and there's always only going to be 3 of them because you need a triangle or 3 edges to create the trio. So the degree, or let's write in black because we're confident about it. So the degree of a trio UVW is 1/2 degree of U plus degree of V plus degree of W minus 3. All right, because this part here will give you the whole degree of the system, and then this 3 will minus out the edges that are part of the trio. So that's not going to be hard. So how can we find the degree of each node? Well, let's go ahead and do that. So first thing we'll do is we'll create a graph and a degree graph, and this one they'll both be default dicts because you know we love default dicts around here. Or no, since n is given, we'll so the graph will be a list, range n. Okay, now I'm getting one of those issues because it starts at 1, and I keep making that mistake. So we'll do n plus 1, and there'll be a 0 node in our graph that just never gets touched. And then our degree, we'll make it a set, and I'll show you why we're doing that in a moment. Again, in range n plus 1. Okay, and then what we'll do is we'll look at each UV edge in edges, and we're going to create this graph. So to create the graph, we say, you know, graph at U has a connection to V, and graph at V has a connection of U. And then the degree of U, we add in V. And the degree of V, we add in U. Now, some might look at this and say, like, you're doing more operations than you need to, but you know, this is 2n space. So I don't really care. There's probably a little bit better, like a little cleaner way of doing this, but you know, I need n space to create G, and I need n space to create degree. That's 2n, it's still n. I'm not going to worry about it if it makes it easier for me to think of the solution. So if I need to later think like, okay, there's probably an easier way where I can eliminate something, but just my intuition is telling me that I want to do both, and hopefully that's the right way of doing it, but I understand that it's a little weird looking. You could do this. Okay, I don't want to start playing this game because then I start doing weird things. Okay, so let's make sure I can run that. Okay. So we're going to do that. All right, and then we have the calculation. So def degree of U, V, and W. So I'm just going to copy the formula exactly. So it's 1/2 times the length of degree of U. We'll just do a sum because we're fancy. Degree of X for length of degree of X for X in UVW. And then we have the -3 for the members of the trio. So this would be the degree of a trio. We'll call it trio degree. Okay, so now we have that function here. So now we're done with finding the degree. We built a graph. We built this degree thing that may not make a total sense why we're doing it. But when we go to part 2, it'll make just, I should have probably done things in a different order. But okay, how do we find all trios? So I kind of did part 2 first because it was easier. But how do we find all trios? Well, I think the only way you can really do this is by, let's look at this example here. So we have 4, we have 1, we have 2, we have 5, we have 3, we have 2 and 3, and 6. Okay, so when we look at this as a graph, this will have neighbors 2 and 3, and this will have neighbors 1 and 5, and this will have neighbors 2. I'm just doing it in the graph form where each node has a list, which is the list of its neighbors. 4 has a neighbor 1, 2 and 3, 1 and 5, and see, I already messed up. This has neighbors 1, 5, and 3. 1, 3, and 5. 3 has neighbors 1, 2, 6. 1, 2, 6. Hopefully I did not forget anything. I probably should have just printed it out from the screen, but whatever. Okay, so how do I know if I found a trio? Well, what I can do is look at a node. For every node, I look at this node and I say, for each of my pairs of neighbors, right? So this is going to take n squared time, which is not great. But for each of my pairs of neighbors, are they also direct neighbors? So I look at my neighbor and I say, hey, are you a neighbor of 3? Right, that's what I asked too. I say, hey, are you a neighbor of 3? Because 3 is my neighbor. And 2 says, yes, I am. I am a neighbor of 3. Yes. Well, if I'm neighbored with 2 and 3, and 2's neighbor is 3, well, then we have a triangle, right? I'm friends with him, and I'm friends with you, and you're friends with him, well, then we're all mutually friends with each other, right? So if I look at each pair of nodes, and I say, hey, are you guys neighbors? Then this system works. So for example, if I looked at 2 now, and I said, okay, I have pairs of neighbors 1 and 5. So I could ask 5, hey, are you neighbors with 1? And it's going to say, no, I'm not neighbors with 1. And since it's not neighbors with 1, that means that there is no trio. Right? Because in order for there to be a trio, there'd have to be a connection here. And if there's a connection there, that means that 5 neighbors with 1, and we have another trio in the system. So to calculate this, it's going to take n cubed time, because we're going to have to look at each node, n nodes, and we're going to have to look at n squared pairs of nodes to make a calculation. And then using the set, we can ask if someone's a neighbor in efficient time. Then using the list, we can look through each pair of neighbors easily. Okay, so let's go ahead and do that. All right, so we're going to look at each node. We don't need to look at node 1. Okay. And then we're going to say for u in range, length of g of node. For v in range, okay, now this is why it's confusing. Okay, for I in range, for j in range, I plus 1, length of g of node. So I'm looking at each pair of vertices. That would mean that uv equals g of I and g of v, or g of node. So these are my neighbors uv. I'm sorry, right, so I'm looking at the node's ith neighbor and the node's jth neighbor. Right, and I'm gonna ask, okay, I'm gonna call this u. Sorry, I just wanna make sure this is all good. And and I'm going to call these VW. Now I'm going to say if W is in degree of U, so this means if my neighbor is neighbors with my other neighbor, then we form a trio, right? So if that's the case, then we're going to have our max min degree equals float. What is it supposed to return? Okay, we'll just put infinity. We say min degree equals min of itself, so if there was another solution, and trio degree of u VW. And I believe that will work. If W in degree of my neighbor, V. So I'm asking if my one neighbor is a neighbor of my other neighbor, then we form a trio. My neighbor's neighbor. Okay, and then we return min degree if min degree not equal float infinity, because if it equals float infinity, that means it never changed, so it never found a value, else -1. There's going to be an error because it's the first time, yeah. Trio. Okay, I need to stick to, someone told me that I need to stick to either camel case or whatever you call the other thing. Spacing with underscores. Oh, I didn't return that. Strange. What's going on here? That's not going to change anything. Okay, so what did I do wrong here? Oh, how embarrassing. So I create the graph U, VU, degree of U add V, degree of V add U. We're going to sum the length of degree, so the number of neighbors that you have for each of these things. It's weird that that works though, that something very wrong is going on here. UI, UJ. So I'm going to do a little debugging here. This is very embarrassing. I thought that this would be right, but I'm definitely missing something. That's what little prints can't solve, you know what I mean? All right. 1, 2, 3, 1.5. Why? Okay, what's the sum of this? Some of this is 9. 1, 2, 3, 4, 5, 6. It should only be 6. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, because I'm an idiot. So my first assertion isn't correct because, okay. So when this thing counts all of its nodes, right? The only ones that get double counted are the ones that are inside the trio, right? So the only nodes that get counted twice are the ones that are actually inside the trio. But the ones that are outside the trio don't get counted twice. So if we just count the degree, these ones will get counted twice. So this will get counted twice, this will get counted twice, and this will get counted twice. So we don't need to divide by 2. The divide by 2 only works if you count every node in the system. But some edges get counted once, some edges get counted twice. Yeah, because I can't believe I didn't notice that. So instead, we can just minus 6. Because all the edges will be counted once, except for the edges that are inside of the trio, which we don't want to count. And since they're inside of the trio, they're going to be counted twice. All right, let's see if this is fast enough. I'm pretty sure that n cubed is the runtime for this. And if I win, I'm going to give myself this little mint right here. Come on. I want the mint. Ooh, that doesn't seem good at all. Seems slow. Time limit exceeded. Come on, man. It's n cubed. What's going on here? So I don't want to say what I'm thinking here until I know it's right, but it's a little heuristic to try to increase the runtime slightly. Maybe get me over the line, hopefully. The idea here is if you don't want to overcount systems you've already tried. Right, so now it only looks at each one once. Right, so it won't overcount. But it's still failing. Why? It's n cubed. Yeah, output limit exceeded. You have to. Come on. So I have an n cubed solution, so why is this not n cubed, n cubed? Okay, so the problem is that this is still n cubed, so the runtime here is kind of unfair. I just quickly looked at something which, you know, gave me the idea. So for list in G, we're gonna say G of U sort. All right, so we'll sort the lists that way that it approaches things. It doesn't reapproach things it doesn't need to approach again. Just a thought, I'm not sure. Come on, man. This is n cubed like the other ones, but it's just not as n cubed. I mean, it's not as pretty. That's why sometimes these TLEs are unfair, because, you know, this is n cubed, but it's not, you know, it's not the perfect n cubed. Me. Imagine doing this in a contest and just being like, this is as fast as it could get. We can do this too. And D is less than min degree. So don't even bother going forward, but that's just an extra calculation. It's not gonna significantly. It is checking if something's in something though. Okay, get rid of this reverse equals true. Sometimes, man. Shoot for the stars, you land on the moon, you know what I mean? Okay, so Okay, this solution works, but it's just not. Okay, so there's a if length of, or we need early termination here. So if length of graph of u is greater than or equal to.
Hey, Mac. You're kidding. I didn't know that. Yeah, if he can wait another 10 minutes, 15 minutes. Okay, I'll get Jeannie on the road and we'll be there as soon as we can. Okay, bye-bye.
Thank you, everybody. Have a good day.